Thank you for reviewing this presentation by GS Plastic Optics on design for manufacturing. The unique nature of injection molding demands a very disciplined approach to the component design. To be successful, developers of optics-enabled systems need to have a comprehensive understanding of the manufacturing process capabilities and inspection equipment available to test polymer optics. In this presentation, we offer a manufacturer's perspective on complex interaction between thermoplastic resins, molds and molding equipment, and metrology involved in manufacturing plastic optics. Let's start with the introduction of GS Plastic Optics.
GS Plastic Optics is a global leader in precision injection molded polymer optics. We provide the enabling components of optics-based devices for medical, defense, machine vision, and augmented or virtual reality markets. We work with optical engineers and program managers to solve complex optical problems using plastic substrates. The result is a competitive product that will maximize our customers' profitability while reducing program risk. Manufacturing capabilities in our vertically integrated factory include expertise in many critical areas: injection molding of precision optical and mechanical components, mold design and flow analysis by our process engineers and scientific molding experts, robotic parts handling systems providing cost control opportunities and 24/7 production, state-of-the-art metrology to ensure conformance to optical, dimensional, and coating specifications, single-point diamond turning machines used for optical mold inserts, prototypes, and low-volume production, coating chambers for application of custom mirror and anti-reflective coatings, optical assembly in our Class 10,000 clean room. The GS Plastic Optics team is proud of our 100-year legacy providing innovative precision plastic optics solutions right here in our Rochester, New York factory. Visit gsoptics.com for more information.
In the course of this presentation, we will review the advantages of plastic optics, discuss selection of thermoplastic resin, explain how the molding process works, demonstrate the online resources available at GS Plastic Optics website, provide guidelines for designing for manufacturing in plastic optics, review quality system and metrology methods appropriate for plastic optics, discuss best practices when working with a polymer optics manufacturer. Design advantages of using injection molded plastic optics over glass include significant weight reduction, the ability to include multiple optical and mechanical features into one part, and the ability to produce large volumes of highly symmetric parts. These advantages can be realized only when the designer is fully aware of the mechanical and optical properties of plastic materials, has good understanding of the injection molding process, and well familiar with the methods to assure that the products are manufactured within the specified parameters. To select the right material for polymer optics, the designer should carefully consider all properties of the thermoplastic resins and how they are compatible with the target application and system performance requirements. Acrylic is one of the most commonly used optical plastics. PMMA polymers are relatively hard and have good mechanical stability. Acrylic is also known for its very good clarity and excellent transmission properties throughout the visible spectrum. However, it has low operating temperature. Polystyrene is generally less expensive than acrylic. The material also tends to absorb somewhat in the deep blue spectrum. Polystyrene has a lowered resistance to UV and is more easily scratched than acrylic. A styrene lens, when paired with an appropriate acrylic lens, offers an effective achromatic solution. High contamination is a potential issue for molded polystyrene optics. Polycarbonate is known for its high impact resistance and the ability to perform over a wide range of temperatures. Because of its high ductility, polycarbonate optics are not easily machined. The resin is more expensive than acrylic. Cyclic olefin polymer, COP, is a family of plastic resins with low native stress birefringence properties and relatively high heat distortion temperature. Zeonex, a resin developed by Nippon Zeon, has a remarkably low water absorption value of less than 0.01%, compared with polycarbonate 0.2% and PMMA 0.3%. GS Plastic Optics has developed considerable expertise in injection molding optics with this resin. OKP is a special polyester for optical use with high refractive index, extremely low birefringence, and high fluidity. It is significantly more expensive than other thermoplastics used for optical molding. More information on materials for polymer optics can be found online at the GS Optics website, www.gsoptics.com. Selecting resources, technical documents, and then properties of materials will bring up the page with links to several PDF documents. One of them is Mechanical Properties of Commonly Used Thermoplastics, which lists coefficient of thermal expansion, operating temperature, water absorption, and specific gravity for optical plastics. Optical designers should note high thermal expansion of the thermoplastic resins. It's about an order of magnitude higher than glass. Thus, maintaining focus over a wide temperature range is a significant problem. They should also consider maximum sustained operating temperature and water absorption of the selected materials to make sure they match product application. The optical properties of commonly used thermoplastics document includes index, Abbe number, DNDT, transmittance, and birefringence data. Thermoplastic materials have a fairly narrow range of index of refraction, from 1.49 for acrylic to 1.61 for polyester. It's important to keep in mind that polymers will exhibit a change in index of refraction relative to temperature. The thermoplastic DNDT is fairly large, about 20 times that of glass, and negative. As the temperature goes up, the refractive index goes down. Some materials, such as polycarbonate and polystyrene, have a high amount of stress to begin with because of their polymer properties. The amount of birefringence in an optic can be exacerbated by poor part design or poor gate location in the mold. Technical documents also include transmission curves. Most optical plastics have high clarity in the broadband visible to near-infrared portion of the spectrum. Individual transmission charts for a large selection of thermoplastic resins can also be found at this web page. One key advantage of polymer optics is the ability to combine optical and mechanical features onto one platform. Mold allows for that to happen. It contains the negative features of the overall shape of the optic, along with any mounting features. It also contains the optical inserts, diamond-turned, plano-polished, or hand-polished, against which the optical surfaces are formed. Molds for plastic optics are specially designed and built to allow producing precision optical surfaces with high dimensional accuracy and uniformity cost-effectively. Molded optics are produced in the injection molding machine or press, which holds the mold, plasticizes the resin, and injects it into the mold cavity. One side of the mold is mounted to the fixed side of the press. The other side is mounted onto the movable platen within the press. During the molding process, the two mold halves are clamped together under high pressure. The molten resin is injected into the mold by the press, and the melt moves through the channels into the tool to the cavities. The cavities fill with the resin and take on the shape of the cavity detail. Once the plastic has cooled to an appropriate temperature, the mold opens and the optics are removed. Injection molded optics should be designed with the manufacturing process in mind. The designer should be aware of the limits of size and tolerances that might be expected of the finished optics. In general terms, overall shape and tolerances of the optic will drive cost and manufacturability. There are some general guidelines. Thicker parts take longer to mold than thinner parts, and optics with extremely thick centers and thin edges are very challenging to mold. On the other hand, a thinner optic presents fewer shrinkage compensation issues and shorter cycle times. Molding cost is directly correlated with the cycle time, which is in turn driven by part thickness and complexity. The technical documents section of the GS Plastic Optics website contains a technical brief on mold-friendly design guidelines, which includes recommendations on making an optical design manufacturable. Also, it contains capabilities sheets listing manufacturing standards for injection molded optics. This table provides a rule of thumb guide describing the limits of fabrication in an ideally designed optic. In the meantime, each part needs to be evaluated on an individual basis. Having good metrology is an absolute requirement when molding optics. Most optical surfaces can be tested on an interferometer. If the surface is aspheric, null correctors can be designed and employed. Another useful device is a contact profilometer, which can be used to trace aspheric surfaces and measure form errors. Because of the common practice of integrating mechanical and optical features into one platform, appropriate metrology is required to assure these features are to print. A coordinate measurement machine is useful for this application. This is especially true if the molded optic has optics in multiple planes relative to a datum. Since injection molding is a volume-related process, the use of functional test equipment is often required and can be tailored for the program needs. Functional testers allow for a go-no-go assessment of the process in a timely fashion. Best practices for the successful program using polymer optics include the following steps: development of preliminary specifications, initial mechanical and optical design concept, and acceptance test criteria. Selection of a reputable optical molder to develop manufacturing strategy, including prototyping plan, ramp up to production schedule, and packaging requirements. Design optimization with guidance from the optical molders engineering team. Development of final product specifications and acceptance test criteria, including 3D CAD files and 2D drawings with all optical and mechanical tolerances. Development of QC metrology strategy, including specialized inspection requirements and functional test setup. GS Plastic Optics has developed a process of assisting our customers with implementing plastic optics solution. We begin each project with a fit assessment process to fully understand your business objectives. We review your product program, market and growth potential, and profitability goals. This process aligns GSPO staff with customer staff to ensure the project is appropriate for molding or diamond turning, and the dimensional and tolerance requirements are achievable. We will verify that we can meet the customer business objectives and schedule. Upon completion of the fit assessment, we provide a carefully planned proposal confirming design and quality specifications, reflecting cost goals and turnaround time.